Good morning, ma'am.
Good morning, good morning. So we were dealing with the lattice enthalpy. It is the amount of energy required to break 1 mole of an ionic compound, solid ionic compound, into gaseous constituent ions. Now we are moving to bond parameters. Bond parameters. You have to write little bit here, bond parameters. What are parameters means on what all things this is associated with. Parameters means variables, bond variables. Number one, bond length. Number one, bond length. Number one, bond length. It is the equilibrium distance between the nuclei of it is the equilibrium distance between the nuclei of two bonded atoms in a molecule. Two bonded atoms in a molecule. Two bonded atoms in a molecule. If it is HI, it will be like this. HI. If it is Cl2 or Cl2, it is like this. This is the bond length. Here, this is the bond length. Equilibrium distance between the nuclei of two bonded atoms in a molecule. Number two, covalent radius. Number two, covalent radius. This we have already learned covalent radius. Covalent radius. So suppose two atoms are made a covalent bond. Covalent bond. So Cl bond Cl, the same thing. Cl bond Cl. Actually, this is so after making the bond, the core will be touching each other, not the outermost shell. In a covalent bond, this core will be touching each other. So here, from here to here, its half is the covalent radius. Write down. In the case of a covalent bond, this is 198. So 198 divided by 2, that is the covalent radius. Covalent radius, this is 198. 198. In the case of a covalent bond, the contribution of each atom is called covalent radius. Covalent radius. Here the bond length is 198. 198 picometer. Here the bond length is 198 picometer. So covalent radius is 99. Therefore, RC, covalent radius, that is 198 divided by 2, that is 99 picometer. Next, van der Waals radius. Next is van der Waals. Next is van der Waals radius. Means when not in bonding. In bonding, covalent radius. Not in bonding. Number 3. Van der Waals radius. This is Now see, two chlorine molecules are touching each other. Two chlorine molecules are touching each other. What is van der Waals radius? See, from here to here, what is the distance? It's half. That will be van der Waals radius. Write down. This is Cl2. This is Cl2. The distance from this to that is 360. That is 360. So it's half. That is van der Waals radius. Write down. RVDW is equal to 360 divided by 2, that is 180 picometer. 180 picometer. Write down. Nucleus is the only hard matter. Now you write van der Waals radius is half of the distance between. It is half of the distance between two similar atoms. Half of the distance between two similar atoms in separate molecules. Two similar atoms in separate molecules in a solid. In a solid. In a solid. Next bond parameter is bond angle. Next is bond angle. Number 4, bond angle. O, H. The angle between two bonds, that is called bond angle. What a molecule has got bend shape or V shape. Bend shape or V shape. So the angle 104.5 degree, that is the bond angle. So write down the definition for bond angle. Angle between the orbitals containing bonding electron pairs. Bonding electron pairs around the central atom. Around the central atom in a molecule. In a molecule. It is expressed in degree. It is expressed in degree. It gives the shape of the molecule. It gives the shape of the molecule. Next, bond enthalpy. Next, bond enthalpy. Bond enthalpy we always write in terms of required. It is the amount of energy required. It is the amount of energy required to break. Just like lattice enthalpy, the word. We always give the definition in the form of required. Write down. It is the amount of energy required. Next bond parameter is bond enthalpy. Bond enthalpy. It is the amount of energy required to break 1 mole of bones, 1 mole of bone, 6.022 into 10 to the power 23, 1 mole of bones of a particular type, between two atoms in gaseous state, between two atoms in gaseous state. H bond H, a single bond. Amount of energy required, bond enthalpy we write in terms of delta HBDE. I can write here BDE. This is the bond dissociation energy. Suffix is BDE, which is equal to 435.8 kilojoules per mole. 435.8 kilojoules per mole. You can simply write delta H. BDE if you write, it is more clear, clarified. If it is a double bond, bond energy, to break this double attraction, we have to spend more amount of energy. So that amount of energy will be greater than a single bond length. So here, delta BDE H, bond dissociation enthalpy of a double bond, that is 498 kilojoules per mole. 498 kilojoules per mole. Now, if it is a triple bond, that is N triple bond N. If it is triple bond, then more amount of energy is required to break this triple bond, triple attraction. We have to break this triple attraction. So delta H, delta BDE, bond dissociation enthalpy here is 946 kilojoules per mole. Bond enthalpy. Now we will see in the case of polyatomic molecules how this bond enthalpy varies. For example, HOH. You see that this OH bond, this is also OH bond. To break these bonds, equal amounts of energies are required. Let's see. To break this bond, means you are breaking the bond between H and OH. You are breaking the bond between H and OH. BDE, that is delta H is equal to 502 kilojoules per mole. Everything is in the gaseous state. This is H2O gaseous state giving OH gaseous state and H gaseous state. For this 502 kilojoules of energy is required. Now you see you are breaking a bond between OH and H. So here when you break, this fellow is in bonding. This fellow is in attraction between with this O. So you have to supply more amount of energy to break. Now you have got this OH. See this OH. Now to break that OH gas to O gas and H gas, the amount of energy required is 427. Delta H is equal to 427 kilojoules per mole. 427 kilojoules. So depending upon the environment, here we broke OH, here also we broke OH only, but dono the environment is different. So due to the difference in environment, same bond will be having different bond enthalpies. So write down. The difference is due to the difference in the environment. The difference is due to the difference in the environment. Next bond parameter is bond order. Bond order. Bond order. Write down the number of bonds between two atoms in a molecule. The number of bonds between two atoms in a molecule is termed as bond order. What is the number of bonds between H and H2? That is 1. So bond order is 1. What is the number of bonds between O and O? 2. So bond order is 2. As bond order increases, bond strength increases. Then it will be very difficult to break the bond. As the number of bonds between two atoms in a molecule increases, the force of attraction is increasing. So N triple bond N bond order is 3. N triple bond N bond order is 3. So we know that to break this triple bond 946 kilojoules of energy is required. Normally it is given. It is this N2 that is broken in upper atmosphere during lightning, thunder and lightning. This N2 is broken over there. So a very high amount of energy is required to break this triple bond. Okay, right on. As bond order increases, bond strength increases. As bond order increases, bond strength increases. Next, resonance structures. Resonance structures or canonical forms. We have already seen resonance structures. Resonance structures. Like ozone. Ozone. You can see a double bond, a single bond. Double bond means double attraction, so the bond strength is more, bond length is less. You can measure the bond length by experiments. You can measure the bond length. So double attraction means this bond should be O double bond, O bond length. It should be O double bond, O bond length. And here it should be O single bond, O bond length. Here it should be O single bond, O bond length. But when we measured by an experiment, we have found that both the bond lengths are equal. That is 128. This is 128. This is 128. We expected a higher to this and lower to this, but both are equal 128. That gave the light to the resonance structures. So we say that this is not pure double bond, this is not pure single bond. It is in between this double bond and single bond, and we show it like this. It's not a pure double bond, pure single bond. So this is called a structure between two structures. What structure? This structure, or the other structure may be double bond here, single bond here, like this. O, double bond here, and single bond this side. So this structure is in between. This structure is in between. This is called resonance hybrid. Resonance hybrid. And this is called the resonance structure, or that is called the resonance structure, or canonical form, canonical form. This is a resonance hybrid, and resonance hybrid has got the lowest energy as compared to the canonical form. So among these two, which has got the lowest energy? Both are having the same energy. The lowest canonical form energy and resonance hybrid energy. The difference between them, that is called resonance energy. This we have explained already. The energy difference between the resonance hybrid and the lowest canonical form, that is called the resonance energy. All right. In the case of carbon dioxide molecule can also have this resonance structure. See, this is carbon dioxide. Both all are having 8 electrons. When this electron enters here, this pair will go there. So what will happen? O, triple bond. So here it is a positive charge, and C, single bond. And here it is a negative charge. So this is a structure. The star structures are not good structures, means the starred structures are unstable. Uncharged neutral ones are stable. Neutral structures are better. They are more stable. Or if you see the opposite way, that is this enters here and this goes here. So you will be getting another structure. First we said electrons are going this way, or you can say in the other direction, electrons are going in this way. So here you will be getting O minus, single bond O, single bond C, then triple bond O, then here O plus. So like this structure. So this is a canonical form, this is a canonical form. Both are unstable, and the stable one is the uncharged structure. That means neutral. So carbon dioxide, any molecule uncharged means least charge separation. Here there is charge separation, is positive and negative. Here also there is charge separation, positive and negative. But here no charge separation. This is the most stable structure of carbon dioxide. Most stable structure of carbon dioxide. Next we are going to polarity of bonds. Polarity of bonds. In a covalent bond, if one atom is more electronegative, then what will happen? Electron density will be pulled towards that. For example, HCl. Like that, it is a covalent bond, but it is a polar covalent bond. Chlorine being more electronegative will be pulling the electron density towards chlorine. So chlorine will develop a delta negative. So I'll be writing like this. Chlorine will develop a delta negative and hydrogen will develop a delta positive. So the bond has become polar. Electron density is more towards chlorine. There is a moment we can say. See this is dipole, 2 poles. So that moment is called dipole moment. Dipole moment. Dipole. This is a dipole, and that moment towards that is called dipole moment. dm. You can calculate this dipole moment, how much moment is towards that Cl. It is the product of one amount. Both the amounts are the same. Suppose this is plus 7, that is minus 7. So you can take that 7 into the distance between them. Dipole moment, write down. Dipole moment is defined as dipole moment is defined. It is a vector quantity towards that direction. So we show it like this with an arrow mark here. This is a vector quantity. It is defined as the product of one charge, means that quantity. Product of one charge, either positive or negative. Bracket means you write either positive or negative. It is the product of one charge and the distance between the positive and negative charges. And the distance between the positive and negative charges. Dipole moment is defined as the product of one charge and the distance between the positive and negative charges. One charge quantity, that is coulombs, and meter, distance, coulomb meter is the unit. Coulomb meter is the unit. And 3.33 into 10 to the power minus 30 coulomb meter is equal to 1 d by, which is equal to 1 ESC. 1 d by or 1 ESC. Suppose I'm giving dipole moment in terms of cm, that is coulombs meter. How will you convert that into d by? You divide that by this 3.33 into 10 to the power minus 30. I'm giving one example. Convert 6.17 into 10 to the power minus 30. 6.17 into 10 to the power minus 30 coulombs meter into d by. D by is shown by capital D. So what I should do? 6.17 into 10 to the power minus 30 divided by 3.33 into 10 to the power minus 30. So I'll be getting 1.85 d by. We always express in terms of d by, 1.85 d by. Okay, next we'll continue in the next class.